All right, so our next speaker is on Zoom. We can see her slides. Her name is Ananya, and she's going to be talking about MPC with asynchronous fallback guarantees.
Yeah, so hi everyone, I'm Ananya, and I'll be talking about this paper, which is joint work with Anirudh and our professor Ashish Chowdhury. So first of all, a quick recap of what MPC is. Let's assume that there are n parties connected to each other over a network, such that every pair of parties is connected by a pairwise authenticated and private channel. Now, each of the parties has a private input, and they want to jointly compute a function of their inputs while ensuring that their inputs remain private. And to do this, they run a protocol. Now, the distrust in the system is modeled by an adversary who can corrupt a subset of T parties, and we assume that our adversary is malicious, which means that it can arbitrarily deviate from the protocol instructions. So traditionally, MPC is discussed in two different types of networks, where in a synchronous network, the parties are assumed to be synchronized by a global clock, and there's a finite time by which messages can be delayed. So protocols in synchronous networks proceed in communication rounds. Now, MPC is possible in synchronous networks as long as up to a third of the parties are corrupt. But in practice, it's really difficult to ensure such strict timeouts. So real-world networks are better modeled by asynchronous networks, where the adversary can arbitrarily delay messages by any finite time. However, the trade-off is that MPC is possible in asynchronous networks only as long as up to a fourth of the parties are corrupt. So a natural question is whether it is possible to design MPC protocols which give security guarantees in both synchronous and asynchronous networks where the parties are unaware of the underlying network type. And we specifically look at the case when the number of corruptions in a synchronous network can actually exceed that in an asynchronous network. Now, we call such protocols which give security guarantees in both types of networks as best of both worlds protocols. We aren't the first to ask this question. The related work can broadly be classified into two different categories, where the first looks at protocols with cryptographic security, which means that the adversary is computationally bounded. And there have been a line of work which have given best of both worlds protocols for various tasks with cryptographic security. Now, the other line of work looks at protocols where the network is assumed to have some form of synchrony. And in our work, we give the highest possible form of security, which is perfect security, and show that we can design an MPC protocol, which in our best of both worlds setting, as long as this condition holds. But we don't show that this condition is necessary, so that is left as an open problem. Now, in order to perform MPC, the parties use the standard shared circuit evaluation paradigm, where in order to share a value, they use a polynomial, which is usually of degree t, such that the secret is hidden in the constant term of the polynomial. And each of the parties holds a point on this polynomial, which is their share of the secret. Now, while evaluating the circuit, each of the values all the way from the input to the output remain secret shared, where a square bracket is used to denote a secret sharing of a value. We use TS degree polynomials for performing our secret sharing because we want privacy in both synchronous and asynchronous networks. And the number of corruptions in a synchronous network can exceed that of an asynchronous network. Evaluating addition gates is easier because of the linearity of the secret sharing scheme, but multiplication gates are harder to evaluate. So we use Beaver strict to do this. And this relies on random TS shared multiplication triple ABC, which means that A and B are unknown to the adversary and C is equal to A times B wholes. So if we do have such an output triplet which is shared, then the output of any gate can be represented as a linear combination of the shares A, B, and C. So everything boils down to how we generate this multiplication triple. And to do this, we use the framework of Chowdhury et al. And realizing this framework, again, has two main challenges. The first is designing a best of both worlds protocol for something called BA, and the other is for something called VSS. And for the rest of the talk, we'll look at what BA and VSS are. And then we will look at the challenges in adapting existing BA and VSS protocols for best of both worlds. And then we will finally look at the high-level ideas which go into designing our best of both worlds BA and VSS protocols. Okay, so to start off, what is BA? Introduced in Peace et al., it was introduced as this thought problem. So let's say that we are in a setting of a war and there are N generals, among which some of them may be spies. So the generals want to agree on whether to attack or retreat from a neighboring kingdom, but they may have differing opinion on this. So the goal of BA is to agree on a common plan. Now, another requirement is that if all the honest generals who are not spies want to attack, or if all of them want to retreat, then the output must be to attack or retreat respectively. So usually protocols have different requirements in synchronous and asynchronous networks. And for BA, we want all the parties to obtain a common output, where if all honest parties have the same input, then that must be the common output obtained. And in a synchronous network, this output must be obtained after a fixed time. In an asynchronous network, however, the output is just obtained eventually with a probability of 1. And this probability creeps into the picture because we want to circumvent the FLP impossibility result. And this is also the reason why existing asynchronous BA protocols don't work in synchronous networks, because specifically when all honest parties don't have the same input, they don't terminate in a fixed number of rounds. Existing synchronous BA protocols don't work in asynchronous networks because they're usually written assuming that messages arrive on time, but this may not be the case in asynchronous networks. Okay, so next, what is VSS? In VSS, or verifiable secret sharing, there is a designated party called the dealer who wants to distribute points on a polynomial to all the parties. And the verifiability guarantees that even if the dealer is corrupt, the points all lie on the same t-degree polynomial. So in a synchronous network, these points must be obtained after a fixed time, where if the dealer is honest, then the points must be obtained on the polynomial the dealer the dealer chose. And if the network is asynchronous, then the points are obtained eventually. And in the case when the dealer is corrupt, they may actually never be obtained because the dealer may never initiate the protocol. So synchronous VSS is possible as long as up to a third of the parties are corrupt, but just like BA, they don't work in asynchronous networks because messages can be delayed. And asynchronous VSS is possible as long as up to a fourth of the parties are corrupt, but they don't work in synchronous networks because you can have more than a fourth of parties being corrupt in a synchronous network. So our contributions in overcoming these two challenges are twofold, where the first is giving a best of both worlds BA protocol with optimal threshold. And this gives all the requirements of a BA protocol in both synchronous and asynchronous networks. Our second contribution is a best of both worlds VSS protocol as long as this condition holds, which gives all the requirements of VSS when the dealer is honest. But when the dealer is corrupt, parties may actually never obtain their output points, even in a synchronous network. But we argue that this relaxation has to be made because the parties are unaware of the underlying network type, so they can't be sure that they will obtain their output after a fixed time. Okay, so we'll now look at the ideas behind instantiating our best of both worlds BA and VSS protocols. And the first step in doing this is designing a related protocol called reliable broadcast, which we'll use as a primitive in both our BA and VSS protocols. So as the name suggests, in broadcast, there's a designated sender party who wants to broadcast or uniformly distribute a message to all the parties in the network. And this has to be done when up to T parties may be under the control of the adversary, including the sender. So in a synchronous network, this message must be obtained after a fixed time, where if the sender is honest, it must be the message the sender intended to send. And in an asynchronous network, the message is just obtained eventually. Now, in either of the networks, broadcast is possible as long as up to a third of the parties are corrupt. And so one might ask why we can't use existing asynchronous reliable broadcast protocols in synchronous networks, because we require the same threshold in both networks. And to understand this better, let's look at broadcast ACAST, which is an asynchronous reliable broadcast protocol. So we won't go into the exact details of the protocol, but it roughly proceeds in 3 different phases and gives all the requirements of a reliable broadcast protocol in an asynchronous network. In a synchronous network, if the sender is honest, then the parties obtain the message after 3 rounds. But if the sender is corrupt, then there may be a difference of 1 round at the times at which honest parties obtain their message. So the reason for this is that in order to output any message, you need to have a required number of ready messages. And when one honest party has a required number of ready messages, the others will get it only in the next round. So to overcome this, we design our reliable broadcast protocol as follows, where first the sender uses ACAST to broadcast his message to all the parties in the network. Then after 3 rounds, which is the time taken by ACAST in a synchronous network, the parties have a first checkpoint where they check whether they obtained a message from ACAST or not. If they did, then they participate with this message as input to any synchronous BA protocol taken as a black box. Otherwise, they participate with the default input of bot. Then they have a second checkpoint where after the time taken by the synchronous BA protocol to run in a synchronous network, they check if they obtain the same message as output from both ACAST as well as the synchronous BA protocol. So if they have, then this is the final output of the protocol. Otherwise, they continue to run the protocol, and the moment they get any messages output from ACAST, that becomes the final output of the protocol. So our reliable broadcast protocol now gives all the required guarantees in both asynchronous and synchronous networks, but we'll specifically look at the case when the network is synchronous and the sender is corrupt, and argue that if any honest party obtains an output at the second checkpoint, then all the other honest parties will also obtain the same output at the same checkpoint. So let's say that there's some honest party who obtained an output M star at the second checkpoint. Now, because of the guarantees of the synchronous BA protocol in a synchronous network, every other honest party will also obtain the same output from the synchronous BA protocol. We further claim that at least one honest party has participated in this protocol with M star, because if this were not the case, then all of them would have participated with an input of bot, and then the output of the synchronous BA protocol would have been bot, but that's a contradiction. So this means that at least one honest party, let's say P1, obtained M star after 3 rounds as an output of ACAST, which means that all the other parties will obtain M star as an output of ACAST after 4 rounds. So by the second checkpoint, everyone will output M star, and that proves what we wanted to show. Okay, so now that we have a best of both worlds reliable broadcast protocol as well, let's look at how we can get BA. And we use the framework of Blum et al. To do this. The first step in doing this is to get a synchronous BA protocol, which also has some asynchronous guarantees. And I'll just go over this very briefly. So as part of this protocol, each party uses the broadcast we discussed in the previous slide to broadcast its input bit. And after the time taken by this protocol in a synchronous network, they check if they've obtained at least n minus t outputs from different sender parties. So if they have, then the majority among these is the output, the final output of the protocol. Otherwise, they output a default value of bot. Now, this synchronous BA protocol has all the required properties of BA in a synchronous network and some additional requirements in an asynchronous network when the honest parties have the same input. So we will now look at how we can bootstrap this protocol to get our best of both worlds BA protocol. And to do this, each of the parties participates with its input bit in the synchronous BA protocol we discussed in the previous slide. And once again, after the time taken by it to run in a synchronous network, they have a checkpoint where if they did not obtain any output as part of the synchronous BA protocol, then they switch to their original input bit. Otherwise, they participate with the output bit in an asynchronous BA protocol, which also has some additional synchronous guarantees. So specifically, these additional synchronous guarantees are that if all the honest parties participate with the same input in this asynchronous BA protocol, then it will terminate at a fixed time. So now, even if all the honest parties did not have the same input initially, after running the synchronous BA protocol, they will all get the same output from this protocol and participate with the same input in the asynchronous BA protocol. Hence, the entire protocol will terminate in a fixed time, and this is how we overcome the challenge of using existing asynchronous BA protocols in synchronous networks where the protocol did not terminate in a fixed time. Now, our best of both worlds protocol also gives all the required guarantees in an asynchronous network as well. Okay, so now that we have both reliable broadcast and BA, let's look at how we can get VSS. But we'll actually not look at how we get VSS, but we'll look at how we get something weaker called WPS, or weak polynomial sharing. And getting VSS from WPS is standard, and I refer you to the papers of Patra et al. And Applebaum et al. To do this. So what is WPS? Just like in VSS, there's a designated dealer party who wants to distribute points on a polynomial to all the honest parties. And actually, WPS is as good as VSS in an asynchronous network, which means it gives all the guarantees of VSS in an asynchronous network. But in a synchronous network, when the dealer is corrupt, not all honest parties may obtain their points. So some of them may not obtain a point at all. And in that case, they output a default value of bot. However, at least TS plus one honest parties do obtain points on the same TS degree polynomial. And this is useful for us because TS plus one points will uniquely determine the polynomial. So the overall idea behind our WPS is that the dealer uses its polynomial as an input in a synchronous WPS protocol. And after the time taken by it to run in a synchronous network, the parties check if they're able to identify a core set of parties such that all the parties in the core set have gotten their points on the same polynomial. So since they may be on having differing opinion on this, they vote on this. And if they agree that they're able to identify such a core set, then they compute the output using this core set. Otherwise, they run an asynchronous WPS protocol and then compute the output using the core set obtained as part of this protocol. So roughly, in either of the cases when an output is computed, all the guarantees of WPS are satisfied. And in the case when the dealer is honest, the parties will always compute their output using the core set obtained as part of the synchronous protocol, and they will never run the asynchronous protocol, which ensures that it terminates at a fixed time. So now, we use the protocol of Ben-Or et al. To instantiate our asynchronous WPS protocol, except that it's slightly modified to handle TS degree polynomials. So we won't discuss this, but we will look at a high-level idea of how our synchronous WPS protocol proceeds. So just as in VSS, even in WPS, we have to do some sort of verification to ensure that honest parties have points on the same polynomial. And to facilitate this, the dealer embeds its chosen univariate polynomial in a bivariate polynomial, which is a polynomial in two variables. And instead of distributing points on a univariate polynomial, it distributes row and column polynomials on this bivariate. So the usefulness of this is that every row polynomial coincides with every column polynomial at one point. So each pair of parties has a point in common, and they can exchange this point to check if they're consistent with each other or not. And furthermore, if for a TS, TS bivariate, if TS plus one honest parties are consistent with each other, then they uniquely determine the bivariate. So first, the dealer distributes the row and column polynomials to all the parties. And this is followed by the parties exchanging that common point and then broadcasting the results, where OK indicates that they are consistent with each other and NOK means that they are not. And in this case, they also broadcast the inconsistent point. So this is followed by the parties constructing pairwise consistency graphs, where an edge in the graph indicates that the parties lying on the edge are consistent with each other. So now, as part of our overall WPS protocol, the parties had to identify a core set such that all the parties in this core set have points lying on the same polynomial. And the dealer is actually given the responsibility of identifying this core set and sharing it with all the other parties in the network. To do this, the dealer first removes parties which broadcasted incorrect points as part of these NOK messages. And then it only considers a subgraph of parties which have sufficient degree. It then checks if there's a structure called an n, ts star within this subgraph. And roughly, an n, ts star is a substitute for an n minus ts clique because finding an n minus ts clique is NP hard, and it consists of two different sets where E and F, where every party in E has an edge to every party in F. So if the dealer is able to find an n, ts star, then this subgraph, the entire subgraph, becomes the core set, and the dealer broadcasts this core set to all the parties in the network. Now, the intuition for why all the parties in the core set are consistent with each other is that the first point ensures that they're consistent in a synchronous network, while the second and third points ensure that they're consistent in an asynchronous network. So this is the broad idea behind our protocol. And I thank you for listening to me, and I'm open to questions now.
Any questions? All right, it looks like we don't have any questions. So let's thank Ananya again